Welcome to 1007 ICT, 1807 ICT, and 7611 ICT Computer Systems and Networks. This is Lecture 10, Internetworking. Last time we looked at the data link layer. We looked at addressing, transmission errors, and medium access control. So basically who gets to talk and when. This time we're going to be looking at the network layer, and we're going to be looking at addressing at the network layer. We're going to be looking at something called subnets. They're a little bit tricky, so we're going to go through some examples of those. We'll look at address resolution, connection-oriented versus connection-less environments, routing, and then devices for connecting in networks. There's quite a lot of stuff here, and again, you could drill down on any of these points and get a lot more detail. So if you're interested in some of these, you'll find lots of information. In particular, things like subnetting, for example. There's a lot of work out there. So in this lecture, you will have gained an understanding of all of these things. So again, there's not so much process-based stuff here, although there may be some opportunities to work with some of this stuff in the workshops. If you're doing any kind of networking related stuff later on, like for example you're interested in the networking major, then things like subnetting will be quite important because it's one of the things that you'll do quite a lot of if you're working with networks. So before we start talking about the networking aspect, why would we want to connect or interconnect networks? Well, a lot of the time we want to connect one local area network to another local area network or to another kind of network. We might have different reasons for doing that. And we're looking at it from probably a corporate perspective at this point, maybe not a home perspective. But if you imagine for the university, for example, we might have more than one corporate division. So we might want to connect those to each other. We might want to separate them because some of them may deal with finances, some of them may be student related, some of them may be staff related, for example. Right? So we might want to segregate those networks for security reasons or other reasons that we might have. We might want to connect two local area networks with different protocols. Can you guys be quiet? Thanks. So if we have two different networks and they speak different languages, we can't just hook them up together. All right? We might need to do something about that. Can you guys be quiet? Thank you. I'm still waiting. Okay, so we might want to connect two local area networks with different protocols. We might want to connect a local area network to the internet. We might want to break a local area network into segments because one of the segments is too congested, for example. And we might want to provide a security wall between different users or different types of users, for example, student, staff, finance, non-finance kind of environments. So there's lots of different reasons why you might want to do this. So it's a fairly common thing to happen, actually, to connect networks together. So when you're connecting networks, you require some kind of network device to join those two networks. And that's because you want to move packets from one network to the other network. We already mentioned that not every network will speak the same language or think about packets in the same way, for example. So you may need to translate different network protocols. And you need to have some way to route the packets between the networks. So I need to be able to understand that things are either on my network or they're on a different network, and I need to be able to access those things regardless of which network they're on. So we need some kind of addressing scheme to resolve that. If you think back to this, and I'll give you the general idea here in terms of when you're sending a letter to someone, I know people don't do that very often these days, but let's say a parcel, right? You're sending something to someone using the postal service, you need to specify the address. When you specify the address, you typically also need to specify the person who it's addressed to. There's an analog there with computing where you need to specify the address. For example, we have things like IP addresses, we have MAC addresses, we have lots of different kinds of address. Another one might be an email address, right? So they're composed of typically the machine or the computer that you want, and sometimes you also specify the user or the port number or the program that you want. Okay. And so there are some example network devices there: hub, switch, bridge, router, gateway. There's a bunch of those. They have different jobs. We'll talk about some of them later on. You also require a network-wide protocol that can handle addressing across the entire network, and this is what this post office model was referring to. If you want to communicate with someone on the other side of the world, well, you need to know what their name is, and something needs to know how to get from where you are to them. Right? So that's the routing part. How do you route packets to their destinations? How do you choose which path to go down? And then perform end-to-end error handling, and that would happen actually not at the network layer but in the transport layer. And that's when you're sending a message, can something go wrong? Yes. Okay, so if something goes wrong, how do you deal with that? Well, we've seen some error detection stuff, we've seen some error correction stuff, we saw forward and backward error correction, yeah, and so we might just say, okay, send me a new copy, rather than having to recompute it and try and fix it. When we're connecting local area networks together, when you're connected to another local area network or to a wide area network, you have to consider a number of things, and here is a number of those: frame format, payload size, data rate, and address bit order. We'll talk about those individually. So the frame format, every local area network protocol will have its own frame format, and so you're going to convert from my format to your format. The payload size. So different protocols will allow different sized data packets or datagrams or whatever they're called at that particular level. And so if they're different sizes, if I've got a really big chunk and your end of the network only accepts little chunks, we're going to have to chop it up. By the same token, if I've got little chunks and you only accept big chunks, I'm going to pad my data out, add more information to fill it up, basically. The data rate, so frames traveling from one network may be faster on one network than on the other network, and so you might have to buffer things. Basically, that means storing stuff for a while until you're ready to actually process it. Address bit order, we've seen this previously. The binary representation of physical addresses varies between protocols. We saw the little endian, big endian sort of variations on this, and so you have to do some appropriate conversion if they're not the same. So you can see some of the issues that we might have to address when we're working with local area networks and connecting between them. So looking at the network layer, it's responsible for getting an individual packet of data from the source computer to the destination computer. Okay, so we're not looking at my neighbor here, but I'm looking at the endpoint. That means I need to know the address or the name of the thing at the other end so I can get to it. So the responsibilities of the network layer, and this is the IP part in the TCP/IP model, is logical addressing and routing. So logical addressing, translate the source and destination addresses into ones that can be understood across all connected networks. We all agree on the naming convention, so that if I send something to a particular address with a particular name, everyone understands that address. We agree on the representation. The routing, I need to determine which path to take from the source to the destination. And this is really important when there are multiple possible routes. So if you're looking at this diagram here, if I'm A and I want to send it to B, well, there's only one route. That's really easy. Okay, what about if I want to send it to D? Well, I've got this one, or this one, or this one. Right? I can find lots of different routes. Now, you might look at this and say, well, look, ABD is obviously the quickest one, and it may be, but it may not be the cheapest. There may be congestion between B and D, for example. So depending on the current environment, maybe A, C, E, D is actually the quickest or the cheapest or the best route. Does that make sense? So you can have different criteria that you apply, and the route might change based on that. So here is a IP header in that diagram on the left. There's quite a lot of information there. Probably the most important stuff for us is the source IP address and the destination IP address. Okay, and so this is me and who I'm speaking to. And on the right there, you'll see how it's put together. You've got the blue data chunk and then the left header chunk, or the headers on the front. Basically, remember the envelope model, you just put some data inside an envelope and you put a stamp on the front saying where it's going to and who it's coming from. So IP, the Internet Network Protocol, is an unreliable connectionless protocol. The packets in this layer are called datagrams, and this is the IPv4 format. So we have a number of different formats for IP. We're still in the middle of using IPv4, but we're transitioning to IPv6. So one of the issues with IPv4 at the moment is we've run out of addresses, so IPv6, among other things, is attempting to resolve that. But we have not yet fully moved over to IPv6. So we're going to focus on IPv4 at the moment, but you'll see over the next so many years, IPv6 will take over. So in terms of network addressing, in order for messages to get to the correct destination, addresses have to be specified. There are three main levels of addressing that's used in a TCP/IP network. You're probably familiar with some of these. You may have seen some of the other ones. But usually as a user, you don't need to see the lower level ones. So for example, the application layer or the user level. I'm using a web browser or I'm an email client. There's some example addresses are www.griffith.edu.au. this is an English address. user@griffith.edu.au, that's an email address. And these are in English, so they're easy for people to work with. The network layer, TCP/IP in this case, or an IP address, might be 132.234.112.9. That's not so easy for people to work with. You might be able to remember a few of them, for example, but if you had to remember all of them and work out which one related to which particular machine, it would be very difficult. So we don't work at that level generally, but you can still type those in, for example, into your web browser, and it will still resolve that in some way as the address. The data link layer, the physical layer, this is the Ethernet example that we're looking at here, is on the right. You'll see there's a bunch of, they look like hexadecimal digits. Okay, we talked about those in the previous lecture. That's a MAC address, and this is to uniquely identify this machine on this local network. Okay, and so you see there's different ways to address things, use different names depending on the level we're working with. Looking at IPv4 addresses in a little bit more detail, so in TCP/IP, the network layer address is called the IP address. You probably have run into IP addresses previously, so they're probably not new. If they are, we're going to go through some more detail about them. 5 classes of addresses are defined to cater for the needs of various organizations. This was done quite a long time ago, and one of the reasons why we've run out of IP addresses, if you look at the scheme here, you've got class A, B, C, D, and E addresses, and they're split into the network ID and the host ID. So the network ID is the name of this network. The host ID is the machine on this particular network, so the host. And you'll see that class A has a very small network ID and a very big host ID on this diagram. I'll show you a different diagram in a second. We'll walk through a bit of this, but you'll see that class B has a slightly bigger network ID and a slightly smaller host ID, and so on, and class C has a bigger network ID again and a smaller host ID again. So we have some range of values here. We're really only interested in class A, B, and C, by the way, for the purposes of this particular course. So looking at that as a diagram, if you have a network part and a host part, then you can split that up in a different way. So class A, we said, had 8 bits for the network and 24 bits for the host. That's 3 bytes. Class B had 16 and 16, and class C had 24 bits for the network and 8 bits for the host. So if we're looking at class A networks, there are, at most, if you've got 8 bits, 256 different networks here. Now I'll just point out that you can't use all 256. Actually, you've got 127, and some of those may be special purpose ones. Like, for example, you might be familiar with 127.0.0.1. It's the loopback address, so it's a special address that you use for a particular purpose. So what I'm suggesting here is that yes, we have 8 bits, but we're not using all of them, so there's less than 256. On the other side, though, we've got 24 bits for our hosts. So on one of these 127 networks, you can have millions of hosts, millions of computers connected to a network. Can you think of a network like that? Probably not. So you can see probably where some of the waste is coming in here. If I've got a class A address, I'm probably not using, I think it's 16 million different computers hanging off this particular network, so I'm probably wasting a lot of those addresses. Does that kind of make sense? Same thing with class B. I've got 16 bits. That's 2 lots of 8, and actually I've got 65536 different networks and 65536 different hosts, assuming we've got the whole range, right? Again, we've got less than this, but I just use the 16-bit value here. So if that's the case, that's a lot of networks, that's great, but every network has 65,536 computers attached to it. Can you think of networks like that? There are probably some large companies, yeah? Do you think there are a lot of companies, if they were given a class B address, that would be wasting some of those 65,000 computers? Absolutely, right? Same thing with class C. We've got 24 bits for the network part, so that's 16 million, let's say, and then we've got 8 bits for the host part, so I can have 256 computers on every one of those networks. This is more reasonable, would you agree? But again, if I'm a small company, I might have 5 or 10 computers. So again, I've been allocated 256. I might not use all of those. Can you see why we might have run out of addresses? Okay, so we need a better scheme, and IPv6 will actually address this because you've got quite a lot more space to work with. But that just kind of illustrates the different classes of network. The other thing I'll point out here with the classes here, so just as a table, Class A has about 16.7 million available addresses for hosts, and Class B has 65,534, Class C 254. You'll notice that they're not exactly 65536 or 256. Some of those are special purpose addresses, or they're used for different purposes, but it's roughly 256 for Class C. And they have a particular address structure, so you'll see there's an address structure column there, and they're grouped in a particular way. So we can tell which one is Class A, Class B, Class C by looking at their address structure. So here's a couple of slides. I want you to review this in your own time, these particular slides. I'm going to show you a synopsis of it just with a diagram. But you'll see here that Class A address, the key thing here is that for the network part, the first bit is a 0. Okay, when you look at Class B, the first bit is a 1, but the second bit is a 0. And Class C, the first 2 bits are 1, and the third bit is a 0. And based on this construction, we can separate the addresses. So as I said, I want you to review those slides in your own time, but I'll show you a drawing of what this is actually, what this looks like. So if Class A has the first bit as a 0, then you have 7 bits left, and those 7 bits could be 7 zeros all the way down to 7 ones. Correct? That's the range, because the first bit is always 0. So what values are they? Well, all zeros are 0. This is the 128 column, so everything full before the 128 column is 1 less than 128, so it's 127. So the range for Class A is 0 to 127. Now we would hope that for the other classes that we don't overlap with this, so the scheme must ensure that. So for Class B, this one is a 1 and a 0. For Class Z, this one is a 1, 1, 0. So Class B, again, we've got 6 bits left. They can all be zeros all the way to all ones. This is the 128 column. So 128 with all zeros is 128. And then 128 with these ones, well, they're all ones, and this is the 64 column. So this is 128 plus 63, which is 191. So the range for Class B is 128 to 191. Does it overlap with Class A? No, they're separate. They're actually right after it, and we would expect that Class C continues on right after Class B. And it does, because our first 3 bits are 110, then we've got 5 bits left. They can be 5 zeros all the way to 5 ones. So 110, 110 in the front of these. 110 with all zeros is 192. 110 with these ones, well, this is the 32 column. So all ones to the right of the 32 column would be a 31. 192 plus 31 is 223. Similarly with Class D and E, I'm not going to go through those, but you can see how just by configuring the first bit, we can identify or uniquely separate our Class A, B, and C environments. So, as I said, just have a quick review of those slides, but what I just showed you on that diagram that captures those slides. Yes? Version 6 has changed that in a number of ways. It's outside of the scope of this course because it actually is quite involved, but basically they're giving you a lot more space, and it doesn't work exactly the same way as well. One of the things that we've done to try and reduce the impact of not having enough addresses is use this idea of subnetworks to split our bigger networks up into smaller networks. All right, so subnets are a method of splitting an allocated IP network address into smaller portions that are identified by a subnet number. So we're basically chopping our bigger chunks up into smaller chunks. So that allows an organization to create multiple networks or subnets within their assigned Class A, B, or C network. Now, it's pretty obvious for a Class A network that you want to chop up your 16 million machines. With a Class C network, well, you've got 256 machines, and maybe you have a couple of networks. You have building A network, building B network, building C network, building D network, right? So you might have 8 networks, for example. If you have 8 networks, technically you would need 8 Class C network addresses. Does that make sense? They're all separate, right? But if you're only using a few machines on each network, well, you can use one single Class C network and then subnet it or subdivide it so that you split it up into smaller chunks. And that's really what we're talking about here. So we use something called a subnet mask. I'll talk about that in a second as a diagram, but we use this to determine the portion of an IP address where its subnet number ends and the host number begins. Okay, so we're still using a normal IP address, but now some bits will refer to the network, some bits will refer to the subnet, and some bits will refer to the host. So a mask is a 32-bit word in this case that has a 1 for all the bits that indicate the subnet and a 0 for all the bits that designate the host. So a mask is ANDed with the IP address to extract the subnet number. So here's a mask example. Again, I'm just going to draw it. I think it'll be clearer if we just have a look at a visual example of it. This is the number 129. So 128 plus 1, 129. It's a nice, simple, easy number. If I AND this with all zeros, my mask in this case is all zeros, what's the answer going to be? 0, 0, 0, 0, 0, 0, 0, and 0. Anything and 0 is 0. So this mask with all zeros blocks everything. Nothing can go through. Would you agree with that? Okay. What about this mask where all the bits are 1? 1 and 1 is? 0 and 1 is? 1 and 1 is? So does this number match the top one? Yes. So this mask lets everything through. Okay? Do you see what a mask is doing? It's selectively letting some stuff through. Now, this one turns it all on or off. Does it have to be like that? No, I can selectively choose which bits I want to let through and which ones I don't want to let through. So this particular mask has 4 ones at the start, and what that will do is it'll let through the first 4 things. It has 4 zeros at the end, which means it will not let through anything on the right-hand side. So the right-hand side will be 0. The left-hand side will be whatever the original number was. Okay, so what does a mask do? It lets some things fall through. It stops some things from falling through. Okay, now you'll notice that I've kept the 4 on the left here. If we have this network, subnet, host, then I would like to let the network part through and the subnetwork part through, but probably not the host part if I want to find out what network I'm on. Does that make sense? Conversely, if I want to find out what host, I want to let these guys through and not the network or the subnet part. So I can adjust my mask depending on what I'm actually after. So we're going to have a look at some network or subnet examples. I've got 2 different examples. There's some in the slides that you can just refer to just as an example on the slides, and then I'll show you a slightly different one on the working out to give you another example or another view at it. So here's a mask example. Given a class C IP address, 192.2.3.130, and I can tell it's a class C address because it's 192, which is the first start of the class C range. How do I determine the network and host ID? Okay, well, let's have a look at that slide. What it's saying is class C, right? Class C means we have 3 bytes for the network part and 1 byte for the host. So these 3 are the network and this is the host. If I want to let the network part through, I need to make my mask all 1s up to the host part. And so on this side, it will all go through 192.2.3. That's the network. And what's my host? In this case, there is no host, it's 0. What about if I want to find the host? I do the opposite. My mask will have all zeros for the network part. Remember, a class C network has 3 bytes for the network. So I'll turn those all off, and then I'll turn all the host part on. And so my network part is 0.0.0, and my host part is, well, whatever the host was. In this case, it's 130. Can you see I can selectively turn things on and off? Great. So we're going to move on to another example, a class B example. So imagine that an organization has a Class B network. They have created 256 subnets using the third byte to denote the subnet number. So normally a Class B network, first 2 bytes are the network. That means you have 2 bytes for the host. What we're saying is those 2 bytes for the host, we're going to chop them up. The first byte is our subnetwork, the last byte is the host. That means we can have 256 subnets, and each of those subnets has 256 hosts. So given that address, how do we determine the subnet ID and the host ID? Well, look at this example. It's the same as the previous one. So you'll see there that we've got Class B address. That means the first 2 bytes are the network. And to get the subnet ID, I need to also incorporate the third byte because that's how we've configured the subnet. So the first 3 bytes are 1s for the mask, and the last byte is 0 for the mask. So what's my subnet? It's the first 3 bytes. In this example, it's 192.2.3, and the host is 0. If I wanted to get the host ID, which bytes do I have to get rid of? The first 3. They're part of the network and the subnetwork. First 2 bytes are the network, the third byte is the subnet. Okay, and so in this case, the machine is 131. Another example here, an organization has a Class C network. They have created 8 subnets using the first 3 bits of the last byte to denote the subnet number. So this is more complicated. We've got a Class C network. The first 3 bytes are already used up for the network. I can't use them for the subnet. They're part of the Class C address, right? So the last byte has 8 bits in it. I can use some of those bits for the subnet. Okay, as long as I'm consistent with that. And I'll start using them from the left. The biggest bits will be the subnet bits. So you have network, subnet, host. So how do we determine the subnet ID and the host ID? Well, you see in this example, and I'll walk through another example in a minute, by the way, to hopefully clarify this a little bit. You'll see that we said we took the first 3 bits in the last byte as the subnet. That means when we have a mask for this, first 3 bytes are the network. The last byte, the first 3 bits are the subnetwork. The last 5 bits are the host. So in that example, you'll see that the first 3 bytes are in red there for the mask to get the subnet ID, and then in bold there's 3 1s for the first 3 bits of the last byte. And what that lets through is just the first 3 bits. The last 5 bits don't get through. And apparently the subnet is 160 in this case, because those are the 2 bits that come through, a 128 and a 32. If I wanted the host part, well, again, it's a Class C network. So Class C has 3 bytes for the network. Because we've got this complication with the first 3 bits being the subnet, if you look at the bottom example there, to get the subnet host ID, I need to ignore the first 3 bytes and the first 3 bits of the last byte. So you'll see that the first 3 bytes are 0s for the mask, and the first 3 bits for the last byte are also 0s, and it only lets through the last 5 bits. So this is machine 14 on a particular subnet. It's a little bit more complicated, right? There's a few things going on here. But the sequence is the same. We have a network, a subnetwork, a host. So let's have a quick look at some examples. If I've got a network, this is a Class B network, how do I know it's 129, which is in the Class B range? 129.6. If I wanted the network part, I would isolate the network part. My mask will have 1s for the network part. There are 2 bytes. The network is 129.6. The host part is nothing goes through, so it's just 129.6. Okay. In this case, I want the host part. So you'll see that I have put 0s for my network, so it's 0.0, and the host is all going through, so 7.3. You notice that this is a Class B network. My host has 2 bytes attached to it, so this is machine 7.3 on this particular network. I have a bit of room here, there. I can use this for a subnet if I wanted to, because I've got a lot of potential machines on this one network. Here is an example of the Class C network with a subnet. So you'll see what I've done here is I have the first 3 bits of the last byte are the subnet. The first 3 bytes are the network, because this is a class C address. That means the last 5 bits are the host on a particular subnet on a particular network in this case. So if I want the network part, I will turn on ones for all the parts that are the network. Well, that's the network and the subnet. So what am I going to get? 193.6, let me do it in line. So 193.6.7, and if I use these 3 ones with that value 110, what comes through? 110, which is, it's 128 plus 64, which is 192. Yes? This is 192. This is the part that makes it confusing because we're working on the left. We're not working on the right. We usually work on the right when we're working with binary numbers. So what comes through is 2 bits, 110. They have a value though, right? They have a value 128 plus 64 because they're the first 2 bits. And so my subnet part is 192. What about if I want the host part, this bit? 0.0.0. And this part is 0 here. Don't let this through. So I just want to get rid of that, I guess. I won't put a 0 there, but this part doesn't go through, but this part does. So what's this part? It's a 1 plus a 4 is 5. So my host is machine 5. And apparently it's on network or subnetwork 192, correct? That's what we worked at before, which is on class C network 193.6.7. As I said, it gets a little bit more involved, mostly because we're using some of these bits for different purposes, but the basic idea is you've got a network, potentially a subnet, and then the host. So moving on to a slightly bigger example, I've got an incoming address, 132.5.4.96. It's coming into my network. It's a class B address, 132.5. I can tell it's class B because it's in the class B range. Now that tells me a couple of things. It tells me that it's 2 bytes for the network and then 2 bytes for the host. On the right, they have subnetted it. From the outside, I can't tell, but on the inside, they will take one of those, the host bytes, and they'll use it for the subnet part. So my request comes in for this particular address. Goes into the router in this case, and it's 132.5.4.96. So I've got 132.5, that's here, and then I want a subnet, because it's been subnetted here, 0.4.96. So it goes to here and it says, is this 0.4? No, it's 132.5.2, so it's not this network. Is it this one, 132.5.4? Yes, this network. Okay, on this network, this is the subnet part, the 4. What's left? 96. Which machine do I want? 11, 1, no, 43, 96, this one. Can you see how it will find its way based on how you've configured things? Again, the person on the outside sending this has no idea that you have subnetted this. They don't care. It's not relevant to them. It's only relevant when you get to that particular network, and they have presumably configured this based on some requirements for this particular network. This may be the staff network, that may be the student network, for example, or whatever the reason is they've configured it like this. Moving on to the address resolution protocol. So when you send stuff to a network, you might need to associate an IP network address with a physical address, the MAC address of a computer on a network. And so there's, in this case, an ARP request, an ARP, address resolution protocol request. And computer says, look, I'm looking for the physical address of the node whose IP address is 141.14.22.1. So for example, I've got this message coming in. It's for a particular IP address. On my Ethernet network, I'm not using IP addresses, I'm using MAC addresses. So I need a translation to say, okay, I've got this IP address, who belongs to it? And they will say, oh, it's me, right, and send it back. And so now I can communicate not on the IP address, but on the MAC address on this network that's related to the IP address that I've been asked to communicate with. It's kind of indirect, right? And it's because we have different ways to name things or address things depending on the network we're on. So what are IP addresses used for? They're used for the global communication. When you get to a particular network, how are you communicating? In this case, a MAC address, right? So there may be differences and you might have to translate. So some of these protocols will do that for you. Switching. We already looked at this. In many networks, rather than directly connecting computers together, they're connected to devices called network switches or multi-point routers. This is from the previous lecture, actually. And we talked about switching, and the idea here is that you have these switches sitting in between computers, and they can switch very quickly from one computer to the next. There's two main types of switching: circuit switching and packet switching. So looking at circuit switching here, the connection-oriented version, it permits any two network devices to talk together at any one time. And this is like the telephone model. All right, so when you're on the telephone, can you both talk at the same time? You can, but you can't understand each other. But it's technically possible. Would you agree? Okay, the technology lets you do it. And it creates a dedicated physical point-to-point connection to exist between the devices for the duration of the communication. Again, when you're talking to someone on the phone, does the order of operations matter? When you speak, should the first letters of the word come out before the last letters of the word? Yes, there's a sequence. It should happen in the same order. So data travels in a continuous stream of bits. There's no sharing of links. Some advantages of this are it's secure and it's most suitable for continuous or streaming or real-time data like your voice communication. Right? It has to be sequential. You have to do it in the same order that you're speaking. The disadvantage is that it's inefficient for typical non-audio visual data. Right? So normal data, it doesn't have to go through the network in the same order. Right? It can just be combined or recombined at the other end without any problems. Okay, for voice communication, that's very difficult. Right? You're going to get garbled communication. So packet switching, any device can simultaneously connect to any number of other devices in the network. It can be either connection-oriented or connection-less. Data is broken up into packets before transmission. This is like a letter. I've got a letter, it's really big, it doesn't fit in one envelope. So I split it up into 5 envelopes, for example, and I send the envelopes separately. Can they get to the destination at different times? Sure. Can they take different paths? Yeah, one might go on one plane, one goes on another plane. And so there's no link between how they get to the destination necessarily, but they will get there eventually. And so this is this environment. So the advantage here is it's more efficient for typical computer data communications. Again, with the letter example, if one airport is really busy, maybe they route around that airport and they go to a different one, right? And so maybe that speeds the process up. The disadvantage of this model is it's harder to secure and it's less suitable for continuous data. Again, because they can go different ways. One of them might go, I don't know, it's supposed to go to Sydney from Brisbane, and it might go through Africa, right? It might get the wrong plane, and eventually it'll get there. But for a voice communication, that would not be a good outcome because the voice communication would be garbled. Okay, and so in this case, the link is shared by packets from different devices. Previous one, you just had one communication stream for that link. Different kinds of packet switching. So data can be delivered across a packet switch network in 2 different ways: connectionless, the datagram model, or connection-oriented, the virtual circuit model. So each packet in the connectionless datagram model travels independently through the network. There's no error control, so if you have a problem with one of the frames, it's just discarded. It's called an unreliable or a best try service. This is the IP model. Remember we said it was, it tries, but it doesn't guarantee anything. The connection-oriented or virtual circuit, it's a logical connection is established between the source and the destination before any packets are sent, and there's a path then. So you have a source and a destination, you know what it is, and you will follow that path. So packets from a single message will travel along the same path, and that's why it's called a virtual circuit. It's not a real circuit, it's just a virtual one we've built as we needed it. So once a single pathway exists for acknowledgements to be made, error checking and flow control can be used. We've got the same pathway, we can now use this to check, did I get the right thing or not? And examples here are the ATM network, for example. So looking at packet switching, connectionless versus connection-oriented services, I think probably it'll be easier to just draw this or look at the diagram rather than just talk to it. So on the top one, connectionless, you'll see what happens here is I've got 1, 2, 3, 4 being sent. So 1 and 2 go this way, 3 and 4 go this way. 3 goes this way, 4 goes that way. 1, 2, 4 will sort of hook up here, and 1 and 2 are first, so 4 comes in after, and then eventually you get 3, 1, 2, 4 at the end. Do they have to be reassembled? They're in the wrong order, so yes, we're going to have to reassemble them. What about the virtual circuit model? I send 1 to the purple one and 1 to the yellow one. They have their own circuit, so the purple one, also the yellow one here follows this one. Yep. And the purple one here follows This one. Are they in the same order? Yes, they're the same circuit, so you don't have the problem that you had up the top with the bottom one. So packets in a session always follow the same path. That means you have to have something called a session, or this idea of continuity, whereas the top one, do you need any continuity? No, you just send stuff and it'll get there, right? Okay, so here's just a diagram, because there's quite a few things we talked about there in terms of switching. This is just kind of showing you the different categories. Switching, you either have circuit switching on the left, which is connection oriented, or on the right you have packet switching, which can be connection oriented or connectionless. Okay, and hopefully this diagram kind of puts into perspective, I guess, how these things are related or not related to each other. When we're talking about routing, it's the process of determining the route or the path through the network that a message will travel in order to get from the sender to the receiver. So how do we determine what path it goes through? So the paths selected for end-to-end data transfer are taken by switching packets onto the correct links at each network node. So we have to know which ones are the correct links, which ones are the ones that are going to get me closer to the destination. Every computer or node that performs routing has some kind of table, a routing table, that's developed by someone, a network manager for example, that specifies how message will travel through the network. There's a routing table there for that particular network. So basically we are looking at node B. This is the table for node B. So where's node B? Here. So node B is directly connected to A, C, and E. So if I want to send something to A, I'm going to use A. That makes sense. I'm directly connected. If I want to send something to C, directly connected, it'll be C. E, directly connected, it will be E. The other ones are more interesting, D, F, and G. And this is where it can vary. So if I want to send something to D, where's D? D's here. Well, I could send A to D, or I could send E to D. Yeah. Now, I might choose one of those over the others based on performance, for example. Maybe one of them is less likely to be overworked. Maybe the other one is, costs more to send it that way. So in this case, we have chosen A. We will take the path through A. In a dynamic environment, maybe over time that changes because that link becomes, congested, for example, and maybe it then becomes E. What about if I want to send something to F? Where's F? F is here. I could use C or E. In this case, we have chosen E. What about G? G is really far away. I could choose C or E, F, C, G. Which one do you think I'm going to pick? Which one's probably more efficient? Just C, because the other one goes through C anyway, right? So I might as well just pick the closer one. Okay, so a person can configure this. That's fine. Or maybe this is configured over time by just seeing how the network performs. Does that kind of make sense too? It can be adjusted potentially. So for routing, the goal is to select the most efficient path through the nodes, and that can depend on a lot of different factors. Performance, so delay, latency we talked about previously. This is where this kind of latency comes in. Number of hops, how many steps you have to go through, how many machines. The node throughput, how busy these particular machines are and how much they're able to put through in any particular time period. The link capacity, how big the links are, how fast they are, whether they're, whether they fall over a lot, that kind of thing. Status and traffic load of individual switches and links. Latency, so the overall measure of the delay incurred in transferring or processing data across the network. And some desirable properties for routing would be correctness. I think probably for routing, it's not just desirable, it's probably mandatory that it's correct. You want to get to the right destination. Robustness is desirable because it's sturdy. Fairness, simplicity, is it easy to compute? I don't want to spend half an hour trying to work out what the best path is, right? Because by that time I could have sent it and it could have already arrived. Minimize the delay, maximize the throughput. There are a number of different approaches to routing. Here's a couple of them: static, random, broadcast, and dynamic. So static, always use the same paths. At the start, when I built this network, I just configured the paths. That's great, it's easy, but it's not very dynamic. If someone adds a new machine, I'm going to have to update this manually, right? So it's not really good for, say, the wireless network here, for example, when you come in with your device. There's no person sitting in a room going, oh, this person's just turned up and I've got to allocate the pathway to it. Random, I could send the packets on any particular path. That will distribute the load fairly randomly or fairly evenly across the network. It might not be very efficient. Broadcast, send the packet on all possible paths. Okay, that's very expensive in terms of the networking, but it will get there very quickly. And then dynamic, adapt to changes in the network. So this is probably the most useful one in terms of the kinds of networks that we're probably thinking of. Some network devices. So in order to switch or route a packet from one host or a network to another one, you need some network devices. Those network devices may need to have different jobs. They may need to translate between different network protocols, and they may need to route packets between networks. We've got hubs, switches, bridges, routers, and an access gateway. You'll see that they go up in complexity, it looks like in those diagrams. So different devices are needed to connect different types of networks. Switches can be used to interconnect segments of a local area network like Ethernet. They're fairly common. Local area network to local area network connections are often performed with a bridge-like device. They're probably not as common these days. Local area network to wide area network connections are usually performed with a router or a gateway. So you have a local area network at home, and you connect to your ISP, your network provider, and you usually have a box sitting there between you and the provider, which does the work to connect to that network. You have also repeaters, and you might have one of those at home if you've got a really big house or you've got some, lots of walls that you've got to go through. And so they're used to extend the length, the range of a physical medium, right? So you can put things further away. So repeaters and hubs operate purely at the physical layer. They regenerate all the signals received on one segment and forward them or repeat them onto the next. And a hub in this case can be considered to be a multi-point repeater. With a hub, basically what you've got here is you've got one message coming in and it floods it out on all the different paths that are available there. Switches operate at the data link layer. They connect different segments of a single local area network together or interconnect two or more workstations. Workstations that connect to a switch each use dedicated point-to-point segments, and that means you can isolate people because they're connected directly to each other, or at least it seems like they're connected directly to each other. So when a packet arrives at a switch, the switch examines the destination address and forwards the frame to the appropriate connection. It doesn't flood it out of every port, for example, or at least usually doesn't do that. Switches versus hubs. So here's an example of the hub. You'll see on the top there is one machine sending stuff to the hub, and the hub forwards it out of all the ports. As opposed to the switch down the bottom, there's one machine talking to the switch, and that switch is only sending it out of one output, which means the other machines could also be sending stuff and dealing with information. Okay, so switches are fast enough to support multiple simultaneous data transfers as opposed to the hub. Bridges or bridge-like devices operate at the data link layer. You can use them to connect two similar local area networks, CSMA-CD to CSMA-CA, for example. Problem with bridges would be that they have to buffer all the frames because they're connecting two different networks, so they can be overloaded. Right? If you have too much information coming in, you can't store it all, you're going to lose packets or frames. And there's also a delay. Routers and gateway are probably the things we're most familiar with in terms of our home network. Right? You have a box that connects to the outside world. Typically it's a router, and they operate at the network layer, and they can determine which is the best path for a message to take between networks. So for your network, there's usually only one way to get out of your network to your ISP. Right? So it has a fairly easy job in that sense. A router can be a special purpose black box computer with several network cards. In an enterprise, the gateway is the computer that routes the traffic from a workstation to the outside network. So slightly different terminology. And in homes, the gateway is the device that connects the user to the internet, your router probably. Here's a bunch of network devices with some networks. So in summary for this section, we had a look at the network layer, addressing, subnets, address resolution, connection-oriented versus connectionless, routing, and devices for connecting networks. I would invite you to have another look at the subnetting part to see how that works and review some of those slides. And that's the end of this section.